Hello everyone. In today's lecture, we'll continue our journey with FIR filters and their design. In the previous lectures, we started to talk about designing digital filters in general, and we have seen that we have two types of digital filters, FIR filters and IIR filters. In FIR filters, the impulse response has finite number of non-zero samples. In other words, it has a finite duration in time. And we have seen that the design of FIR filter can either happen in time domain using the windowing method or the frequency domain using frequency sampling method. In today's lecture, we will start to talk about the windowing method. In the previous lecture, we started with the frequency response of an ideal low-pass filter with linear phase, which took the form e to the negative j alpha omega, when modulus omega is larger than 0 and less than omega c, and 0 if modulus omega is larger than omega c and less than pi. And then we used the inverse discrete time Fourier transform in order to find the impulse response h desired of n, which took the form of a sinc function sine omega c n minus alpha over pi n minus alpha, extending for n from minus infinity to positive infinity. This is the famous sinc function with the peak or the maximum value happening at n equal to alpha. And as we have seen in the previous lecture, this impulse response implies that this filter is not FIR, it does not have a finite duration in time domain, and it's not causal because it has samples before n equal to 0. And we have discussed three cases where the first case was 2 alpha is an even integer, which means alpha is an integer like this case. So the maximum value of the sinc function would happen at n equal to alpha, n equal to 3 in this example, and the samples before and after will be symmetric. So in this case where 2 alpha is an even integer or alpha is an integer, in this case the impulse response has symmetry, and this symmetry is linked to the phase linearity. The second case was when 2 alpha is equal to an odd integer, which is equivalent to having alpha equal to an integer plus half. And again, in this case, the peak or maximum will happen at alpha, which is integer plus half, but we will not be having a sample at alpha. Instead, the samples before and after, which is alpha minus half and alpha plus half, will also be symmetric, and we have the symmetry in the impulse response, and this symmetry again is linked to the phase linearity. If you want to have a filter with linear phase, you have to keep the symmetry in the impulse response. The third case where 2 alpha is not an integer, in this case, as we have discussed in the previous lecture, we will lose the symmetry in the impulse response, and hence we will lose the phase linearity. And also in the previous lecture, we have seen that m, which is the maximum index of the impulse response extends from 0 up to m is equal to 2 alpha. So in this case, as you can see, this is the desired impulse response extending from minus infinity to positive infinity. If we want to make this filter to be a causal filter, we need to neglect or ignore the samples before 0. And if we want to keep the symmetry in the impulse response, we have to ignore or neglect the samples after 6, which is m. So basically, because the sample at 7 was symmetric with the sample at minus 1, and the sample at 8 was symmetric with the sample at minus 2. So if we are going to ignore these samples at minus 1 and minus 2 and minus 3 in order to keep this filter causal, we need to ignore the samples starting from 7, 8, 9 and so on in order to keep the symmetry in the impulse response. That's why the desired impulse response now will be truncated. We will ignore the samples before 0. We will ignore the samples after 6. We'll only keep the samples from 0 to 6. And again, 6 is equal to 2 alpha. So if alpha is 3.5, m will be 7. So we'll keep the samples from 0 up to 7 and so on. This is basically equivalent to multiplying this desired impulse response with this kind of window, Wn, which has a value of 1 from 0 up to m, and 0 otherwise, multiplying the desired impulse response, which extends from -infinity to +infinity, with this window will kill the samples at -1, -2, -3 up to -infinity, because it's multiplied by a 0, and it will kill the samples starting from 7, 8, 9, and so on, and will only keep the samples from 0 up to 6. So this truncation process we have been talking about, killing the samples before 0 and after m, is equivalent to multiplying the desired impulse response, h desired of n, by the window w of n. And this will give us the impulse response h of n of the practical filter which we can implement. A practical filter which approximates the desired filter response we want. But as you remember, multiplying sequences in time domain results in convolution in frequency domain. Maybe we did not study discrete time Fourier transform in details, but multiplying discrete time sequence will result in what's called periodic convolution in frequency domain. We will not go through the mathematical details of periodic convolution, but enough to say it's kind of similar to the convolution, the linear convolution we have seen before. Only few differences, but in the general concept it's almost the same. So multiplying h desired of n by this window, which is called the windowing operation, that's why this method is called designing FIR filter by windowing, will give us convolution in frequency domain. So the desired frequency response of the filter, which was the ideal filter, will be convolved with the spectrum of this window, which means that the spectrum of this window will affect the resulting spectrum of the approximate filter we have over here. Let's go back to our slides and go through this in more details. So the easiest way to obtain an FIR filter is simply to truncate or kill or remove the samples or the impulse response of an IIR filter, which is basically killing the samples before 0 and killing the samples after m. That is equivalent to using a rectangular window, as we have said before. Multiplying this h desired of n by this rectangular window will give us this truncation effect we are looking for. Okay, so although this truncation will minimize the mean square error, and there is a mathematical proof for this statement that the mean square error, which is the error is the difference between h desired of e to the power j omega, the desired frequency response, and h of e to the power j omega, the approximate frequency response. The rectangular window will minimize the difference between these two in the mean square error sense. But we have a major drawback over here, as we're going to see, that the resulting filter has unacceptable ripples. As you remember, in practical filters we have these fluctuations in the pass band and fluctuations in the stop band. This is called the ripples, and using a rectangular window will give us unacceptable ripples. So let's move on and see how it goes. So the windowing design approach, in this windowing approach thing, we tend or try to reduce these ripples to a desired level by applying a non-rectangular window to the impulse response. However, the filter obtained will no longer be optimum in the mean square error sense. So let's go back to our whiteboard over here. So here we are using a rectangular window. So multiplying the desired impulse response over here by this rectangular window will truncate the sample, will kill the samples before 0, will kill the samples after m, and this will give us a finite impulse response filter which is causal. But using a rectangular window like this one will give us unacceptable ripples. So the windowing method tries to use another windows, a different kind of window which is not rectangular, in order to reduce the ripples that we are going to get. Okay, so the windowing design approach reduces these ripples, which was unacceptable. So using a rectangular window will give us unacceptable ripples, But to reduce these ripples, we apply non-rectangular window instead of a rectangular window. Okay, so let's start first with a direct truncation of ideal impulse response, which is equivalent to using an ideal or a rectangular window. So this is a frequency response h desired e to the power j omega, which is a discrete time Fourier transform of the impulse response. And here in this slide and the next few slides, we will be actually using some details of the discrete time Fourier transform which we did not study. So I will just skip slide number 20 and slide number 21, and I will go to the conclusion in slide number 22. So after few mathematical steps which we did not go through in details because we didn't study the discrete time Fourier transform in much details, the optimum choice for the impulse response h of n would be to take the samples of h desired of n from 0 to m and 0 otherwise. So this equation is simply saying that we have a desired impulse response extending from minus infinity to plus infinity. In order to make this filter causal and linear, to have a linear phase, h of n should be equal to the desired impulse response only for the time instance from 0 up to m and 0 otherwise, which is equivalent to ignoring or killing the samples before 0 and killing the samples after m, which is equivalent to multiplying with this rectangular window. Okay, so that is multiplying the desired impulse response by a rectangular window which has a value of 1 from 0 up to m and 0 otherwise. So the process of designing FIR filters would be summarized as follows. We start with a desired frequency response, the ideal frequency response, ideal low-pass filter with linear phase. Then we use the inverse discrete time Fourier transform to find the desired impulse response. As we've said before, the windowing design happens in time domain. That's why we take the frequency response, move it back to the time domain to get h desired of n. And then we apply a window. In the simplest case, a rectangular window, which is equivalent to truncation of the impulse response. That's to kill the samples before 0 and kill the samples after m. This will give us h of n, the approximate impulse response of the filter we have. Okay. In order to understand how this truncation will affect the frequency response, let's start by realizing that h of n, the approximate impulse response, is equal to the desired impulse response, h desired of n, times a window w of n. Again, if you multiply this desired impulse response extending from minus infinity to plus infinity by this rectangular window, which has a value of 1 only from 0 up to m, this will give you the effect of truncation you're looking for, killing the samples before 0 and killing the samples after m. So, using the DFT properties, multiplying two sequences in time domain is equivalent to what's called the periodic convolution. As we can see over here, when you multiply the sequence h desired of n with the sequence w of n, this is equivalent to doing periodic convolution in frequency domain between the discrete time Fourier transform of the desired impulse response and the discrete time Fourier transform of the window, which are h desired of e to the power j omega periodic convolution with w of e to the power j omega. This will give us the frequency response of the actual filter h of e to the power j omega. And here we can see that the frequency response of the practical filter we can implement is the periodic convolution of the desired frequency response and the window. And here we can understand that the window, the choice of the window, will affect the frequency response of the filter we have over here. We didn't study the periodic convolution, but the equation goes like this. The periodic convolution is 1 over 2 pi integration from minus pi to pi h desired e to the power j theta w e to the power j omega minus theta d theta. If you take a closer look at this equation, this is very similar to the linear convolution we used to learn in the previous courses, but it's only from minus pi to pi instead of having the integration from minus infinity to infinity. So without going into much details, think about periodic convolution as some sort of linear convolution but with slightly different mathematical details. So the approximation frequency response h of e to the power j omega is the periodic convolution of the desired ideal frequency response and the Fourier transform of the window. The Fourier transform of the window has this form, it's sine over sine, and the derivation is simple. You can start by doing the discrete time Fourier transform. So w of e to the power j omega is a summation from n going from minus infinity to positive infinity. The function we have, which is w of n e to the negative j omega n. But since the window we have is 0 for all n except from 0 up to m, so the summation will go from 0 up to m e to the negative j omega n. And moving on, we have two values for this summation. If omega is equal to 0, e to the power 0 is 1. So you're summing 1 from 0 up to m, it will give you m plus 1. And otherwise, it will be a summation of r to the power n, which is 1 minus r, and here 1 minus r to the power m plus 1. And going through the mathematical steps over here, so in the denominator over here, if we take e to the negative j omega by 2 as a common factor, we will have e to the power j omega by 2 minus e to the power minus j omega by 2. And in the numerator, if we take e to the negative j omega m plus 1 all divided by 2, like in this case, we will be having e to the power j omega m plus 1 over 2 minus e to the negative j omega m plus 1 by 2. And this term over here is simply 2j sine, and this term over here is another 2j sine. So simplifying, we will get sine omega by 2 m plus 1 over sine omega by 2. If we try to plot this spectrum, which is the spectrum of the window, it would look like this, something like a sinc function, but it's periodic right now. And we have this large fluctuations over here. So now, in order to get the frequency response of the practical filter we have to convolve this w e to the power j omega, the spectrum of the window, with the desired frequency response, which is the ideal filter. So doing so, as you can see over here, this curve is the ideal filter, which is being convolved with the spectrum of the window we have. And convolution implies shifting and integrating. The resulting spectrum, with the resulting frequency response of the practical filter, would look like this. Instead of having a flat response in the passband, we will have this kind of ripples. Instead of having a sudden change from passband to stopband, we will have a gradual change. Instead of having a flat response in the stopband, we will be having this kind of ripples, which are the effects we have already discussed about the practical filter. This is the result of the periodic convolution of the frequency response of the ideal filter with the frequency response or the frequency spectrum of the window we have. So now we can understand and realize that the choice of the window will greatly affect the ripples we have in the passband, the ripples we have in the stopband, and the transition band. So the resulting response after truncation in time domain will be the convolution, the periodic convolution will have ripples in the passband and in the stopband, and it will have also a gradual transition band. The passband ripples and stopband attenuation resulting using a rectangular window, which is a direct truncation of the impulse response, are unacceptable for practical applications. That's why we can use another or different shapes of windows. And instead of using rectangular window, we can use another shapes of window. And using different shapes of windows will affect the passband ripples and stopband attenuation and the widths of the transition band. Using non-rectangular windows to obtain a less abrupt truncation of the impulse response will reduce the height of the ripples at the expense of a wider transition band. What is this supposed to mean? If we go back to our whiteboard over here, as you can see, the rectangular window we have been using has a sudden change at 0. So basically, instead of now we have a sample of a value 0 at -1, and next we have a sudden change, a sample value of 1 at 0. This sudden change over here results in large ripples. Same over here, we have a sudden change at the last sample. From having a value of 1, suddenly it will become a 0 at instant 7. So this sudden change will result in large ripples, in large fluctuations in the frequency spectrum over here. So that's why we're hoping by using different windows which has smooth transition, over here, and instead of having this sudden transition, we'll be having a smooth transition. Hopefully this smooth transition will result in less ripples, less fluctuations in the frequency domain. So the statement simply says that using non-rectangular window to obtain a less abrupt truncation, instead of having a sudden change in the window from 0 to 1, we'll have a gradual change. This less abrupt change will reduce the height of the ripples in the frequency domain. The most commonly used windows are rectangular window, which is the one we have seen before, the Bartlett window, or it's called the triangular window, Hahn window, Hamming window, and Blackman window. In MATLAB, you can generate this window using the following commands: rectwin, Bartlett, Hamming, and Blackman. And you just give the command over here, the length of the filter, L. As we know, L is equal to M plus 1. So the relation we know is that M is equal to 2 alpha, right? So M is equal to 2 alpha, and the length of the filter L is equal to M plus 1, which is 2 alpha plus 1. So you only give the MATLAB command L and it will give you the corresponding window. So Bartlett of L will generate a Bartlett window of length L, which has alpha equal to L minus 1 over 2. And these are the equations for the Bartlett, Hahn, Hamming, and Blackman. We do not need to memorize these equations. Maybe we only need to take a look at the plot of these equations. So all of these equations, all of these windows, Bartlett, Hahn, Hamming, Blackman, have the same feature of a gradual transition. And instead of suddenly jumping from 0 up to 1 in a rectangular window, we have a gradual transition from 0 increasing gradually up to the middle of the window duration and then decreasing gradually again. This gradual transition will reduce the ripple size in the frequency domain and hence will reduce the ripples we have in the pass band and stop band. The Bartlett is a triangular window, so it's a straight line from 0 up to the middle part of the window duration, and then it goes down again as a straight line. Hamming and Hahn and Blackman are different variations of sine and cosine. As you can see, Hahn, Hamming, and Blackman are mainly cosine and sine windows, gradually increasing and decreasing. The one important feature we need to observe over here is that we have a symmetry in the window. Remember that we needed to have a symmetry in the impulse response, that h of n is equal to h of m minus n. The same symmetry is satisfied and must be satisfied in the window, because if you go to our whiteboard over here, as you can see, the new impulse response is equal to the old impulse response times the window. So if the old impulse response, the desired impulse response, is symmetric and the window is also symmetric around alpha, so the new impulse response will be symmetric. So we need to keep the symmetry in the window, which means that since we have a condition that says h of n should be equal to h of m minus n, which is a condition for type 1 and type 2 linear phase filters, we also need to have the same condition for the window. So w of n should be equal to w of m minus n, which means we have sort of symmetry in the window. This way, when we multiply the window by the desired impulse response, we'll get a new impulse response which is also symmetric in the same manner as we have discussed before. So moving on, this is the spectrum of the different windows. So as you can see, the rectangular window has higher side bands. This part of the spectrum, we call it a side band. So the side band is largely higher than minus 50 decibel. It's almost in the order of 25, minus 25 or so. But here, talking about a Bartlett window, the Bartlett window gradually approaches minus 50, so it provides better stop band attenuation. Here, the Hahn window has better and better stop band attenuation, but it's not uniform. It kind of starts at minus 30 or so and gradually decreases. The Hamming provides almost a constant or flat minus 50 decibel attenuation in the stop band, and the Blackman it's even minus 60 or so. So as you can see, using different windows will provide different levels of attenuation in the stop band, different levels of ripples if you wish. So, and here we emphasize the fact that these windows are always symmetric, that is W of n should be equal to W of m minus n for the entire duration of the pulse, which is from n equal to 0 up to n equal to m. Therefore, the windowed impulse response, which is the multiplication of the window times h desired, has the same symmetry as the ideal impulse response h desired of n. In other words, windowing an FIR filter with linear phase does not change its type. Since we have the symmetry in the window, we will have a symmetry in the new impulse response, and then we still have the linear phase. So, in order to wrap things up over here, we need to put clear steps in the design process. So the first process, we will start with the specification, which are mainly omega p, the edge of the pass band, omega s, the edge of the stop band, AP, the allowed ripples in the pass band, AS, the stop band attenuation. And of course, we have discussed three types of specification: the absolute specification, relative specification, and analog specification, and we have learned how to transform one kind of specification to the other. So given the specification in any form, we need to find delta P, the fluctuations allowed in the pass band, delta S, the fluctuation or the attenuation in the stop band, and we choose a new delta, which is the minimum of delta P and delta S. So we'll design on the smallest one of delta P and delta S. So let's say in the pass band we are allowed to have fluctuation plus minus 0.1, whereas in the stop band we're allowed to have a maximum of 0.005. So we'll use the minimum value as our delta, which will be used in the design, which is 0.005. So next step is to determine the cutoff frequency of the ideal low-pass filter. Given omega p and omega s, we assume that the cutoff frequency is in the middle between omega p and omega s. So it's 0.5 omega p plus omega s. Now we will use this new delta in order to get the new stop band attenuation, which is minus 20 log delta. If delta s is the minimum one, so this new A will be equal to AS. If delta P is the minimum one, so the new delta will give us a new stop band attenuation. And also we can define the width of the transition band delta omega to be omega S minus omega P. Next step, we have a table from which we can choose the window function. Based on what? Based on the stop band attenuation A. We'll choose the window which provides the smallest stop band attenuation greater than A. So this statement will be made more clear in the next example. So based on the new value of stop band attenuation which we found using the new delta, which is the minimum of delta P and delta S, now we can choose the window from a given table. This table will be given, and we can choose the window based on the new stop band attenuation. We choose the window which provides the smallest stop band attenuation greater than A. And for the chosen window from the table, we'll have an equation for delta omega. So now we know delta omega is equal to omega S minus omega P. In the table, we will have an equation relating delta omega to the length of the filter. Once we know the length of the filter, we can get m, which is L minus 1. Once we know m, we can get alpha, because alpha is m by 2. Of course, if m is odd, this means we have a type 2 filter. If you want it to be a type 1, you just increase m by 1. Increase m by 1, this will give you a type 1 filter. So this is the table we're going to have in the exam. It's basically stating the different types of windows over here with the value of stop band attenuation AS and the equation for delta omega. We will use the exact equation. Here we have an approximate equation. Here we have an exact equation. This table was basically derived using the fact that the spectrum of the window will affect the ripples. So for every one of these windows, we can do Fourier transform, get the spectrum, do periodic convolution, and see what kind of ripples we're going to have in the pass band, in the stop band, and what kind of transition band we have. The observation here is that moving from rectangular window to Bartlett to Hahn, Hamming, and Blackman, the stop band attenuation is getting better and better, higher and higher. So if your application requires higher stop band attenuation, probably you will be using one of these windows like Blackman or Hamming towards the end of the table. But this comes at a price. The price is basically a wider transition band. So for the same L, if we assume L, the length of the filter is the same, the Blackman has a delta omega of 11 pi over L, whereas the rectangular window has the smallest transition band, 1.8 pi over L. So again, there is no free lunch. If you want better stop band attenuation, less ripples, less fluctuations, you need to pay a price, which is basically a wider transition band. If you have a requirement on a transition band that's not that wide, a smaller transition band, you need to allow for larger ripples or larger fluctuations in the pass band and stop band, and you need to allow for less stop band attenuation. Okay, next step, we need to determine the impulse response of the ideal low-pass filter, which is the form we have derived before, sine omega c n minus alpha over pi n minus alpha, and of course alpha is m by 2. Once we have this desired impulse response, we need to multiply it by the window we have chosen based on the new stop band attenuation from the table. Once we have this new impulse response, we need to verify that this kind of impulse response actually satisfies the requirements. So we need to put it in MATLAB, get the frequency response, and so on. If it's not satisfying the requirement, we go back to step 6. In step 6, we need to use different lengths or different alpha, increase basically the length of the alpha, and then we can change the window type. So we check whether the design filter satisfies the prescribed specification. If not, we increase the order of the filter, M, increase it by 1, and go to step number 6. If not satisfied, we may need to use a different window with a higher stop band attenuation, and so on. So let's try to solve this example and see how it goes. So here we are asked to design a low-pass linear phase FIR filter with the following specification. Omega p, the edge of the pass band, is 0.25 pi. Omega s, this is a mistake over here, this should be omega s, equal to 0.35 pi, which is the edge of the stop band. AP, the allowed pass band ripple, is 0.1 dB, and AS, the required stop band attenuation, is 50 dB. So let's move to our whiteboard over here. So we have omega p, omega s, AP, and AS. These are the 4 specifications we have. First step is we need to find delta p and delta s. So as we know, AS is approximately equal to minus 20 log delta s. From this equation, we can directly find the value for delta s. And AP is equal to 20 log 1 plus delta p over 1 minus delta p. So again, we can use this equation to find values for delta p and delta s. So going back to our slides, we can see that delta p will be 0.0058 and delta s will be 0.0032. So let me write this down. So delta P will be equal to 0.0058 and delta S will be equal to 0.0032. So this is the first step. Second step, we need to choose the minimum value of these two. So we'll define a new delta, which is the minimum value of these two. As you can see, the value of delta S is the smallest one. So delta is equal to minimum of delta P and delta S, which will be in this case delta S. Then we need to compute the new stop band attenuation A, which is minus 20 log the new delta we have chosen. And since delta is equal to delta S, the new value of A, which is minus log 20 delta, will be minus 20 log delta S, which is the same old stop band attenuation AS. So A will remain to be 50 decibel. This is the new stop band attenuation. But again, if at any example we have, or any problem we have, delta P is the minimum one. So delta will be equal to delta P. In this case, minus 20 log delta P will give us a new value for the stop band attenuation, which is different from this value of AS. Next step, we need to find omega C and delta omega. So basically, omega C, the cutoff frequency, is assumed to be halfway between omega P and omega S, which is basically omega P plus omega S by 2. And looking at the numbers we have over here, so 0.25 plus 0.35 will give us like 0.6 pi by 2, so it's 0.3 pi. So the cutoff frequency is 0.3 pi. And delta omega is the difference between omega S and omega P, which is the width of the transition band. And omega S minus omega P will give us like 0.1 pi. So now we have omega C, delta omega, delta P, and delta S, and the new stop band attenuation. So let's go back to our slides over here. So first step, we'll choose delta to be the minimum value of delta P and delta S, which is delta S. And then we get the new stop band attenuation, which is minus 20 log the new delta we have, which is 50 decibel, same as the old stop band attenuation. And omega C 0.3 pi and delta omega 0.1 pi. Next step, we need to choose a window based on this new stop band attenuation. In order to choose a window, we need to go back to this table. So from this table, which window would provide us with the 50 decibel stop band attenuation we need? If you remember, we need to have a filter whose stop band attenuation, the new value A, is equal to 50 decibel. So looking at AS, which is a stop band attenuation, we only have two candidates. We can either use a Hamming window or a Blackman. Both windows will give us a stop band attenuation of 53 and 74, which are larger than the 50 decibels we want. That's why if we go to the statement, it was a bit confusing over here, we choose a window which provides the smallest stop band attenuation greater than A. So in this example, A was 50 decibel. So first step, we'll find which windows will provide us with a stop band attenuation greater than A. In our example, we have 50 decibel, so we can choose either the Hamming or Blackman. So which one to choose? We can choose the Hamming window. It will give us 53 decibel, so it will satisfy the requirement of minimum 50. And we can also choose the Blackman, which will provide us with 74, even better, stop band attenuation. But again, keep in mind that having better stop band attenuation will have the side effect of having a larger transition band. Or if you want to have the same delta omega, in our problem, which is 0.1 pi, we will have a longer filter. So let's go to our whiteboard. Let me just write down for a second. So if we choose a Hamming window, or a black man window? What would be the difference? In order to understand this and to choose a proper window, let me just write down the equation for delta omega. For a Hamming window, delta omega, as you can see over here, the exact value is 6.6 pi over L. 6.6 pi over L. And for a black man, delta omega is equal to, for a black man, 11 pi over L. So, going back to our whiteboard over here, so these two windows, the Hamming and black man, will satisfy the 50 decibel requirement. And now, since we have delta omega equal to 0.1 pi, so if you put 0.1 pi equal to 6.6 pi over L, in this case, for a Hamming window, you will get a filter of the length 66. Whereas for a black man, you will get a filter of length 110. So, if you remember from our previous discussions in the previous lectures, we always tend to use filters with minimum order or minimum length. So in this case, choosing a black man filter would be an overkill. Yes, it will give us 74 decibel stop band attenuation, which is much higher than the requirement, 50 decibel, but it will give us a very long filter of length 110. Long filter means longer delays, large number of hardware multipliers and delays in order to implement this filter. But on the other hand, using a Hamming window will give us the required stop band attenuation, which is 53, which meets the requirement, with a shorter filter of length 66, almost half what we would have in a black man. That's why we will choose a Hamming window in this case. And now we can read the confusing statement one more time. So we will be choosing the window that provides the smallest stop band attenuation larger than 50. So we have two windows, the Hamming and black man, providing stop band attenuation larger than the 50 decibel we have. We will choose the smallest one, which is the Hamming, providing 53, because the smallest one larger than 50 will give us a shorter filter and hence a less complicated and less expensive filter with less delay and so on. So this is about choosing the window based on the stop band attenuation. Okay, so going back to our example, so from the window we choose a Hamming window, and then we can use delta omega, which we have, which is 0.1 pi, and use the equation we have from the table. For the Hamming window, we'll get a filter of length 66. So moving to our whiteboard over here, so we have a filter Hamming window of length 66. As you remember, L is equal to M plus 1. So if L is 66, L is equal to M plus 1. So L is 66, it's M plus 1, which means that M is 65. And in this case, M is odd integer. Odd integer will give us a type 2 filter. In this question, we didn't have a requirement to design a type 1 or type 2, so we can just leave it as is. If we leave it as is, so M will be 65, which is 2 alpha, which means that alpha would be 65 by 2, which is 32.5. So as you can see, alpha here is an integer plus half. And in this case, the impulse response would look like this. So H desired of N would be sine omega C. If you remember, omega C was 0.3 pi times N minus alpha. So N minus 65 by 2 over pi times N minus alpha, N minus 65 by 2. and this would be the impulse response, the ideal impulse response. But of course, since we are using a Hamming window, as we have seen over here, the actual frequency response will be equal to the ideal frequency response multiplied by a Hamming window. And this will be the problem we have. So on MATLAB, you can have this equation, you can have a Hamming window, and then you can get the impulse response, you can get the frequency response, and so on. But if the requirement was to have a type 1, if the question was asking for a type 1 filter, in this case, we need to change M. So we will let M to be 65 plus 1, we'll make it 66. We increase M by 1, which will make it an even integer, which will make alpha to be integer, to be 33, and in this case we will get our filter, which was of type 1 filter. And in this case the impulse response will be sine 0.3 pi n minus 33 over pi times n minus 33, and again we will be using a Hamming window. So let's move back over here. So if we have L equal to 66, so M is 65, this will give us type 2. If you want to make it type 1, we will make M equal to 66. In this case it's type 1 filter, and alpha is 33. So the impulse response will be sine 0.3 pi times n minus 33, which is alpha, over pi n minus alpha. And the actual frequency response will be the desired impulse response times the Hamming window. If we try to do this in MATLAB, this will be the impulse response we'll be having. It will have a sample at 33, and it will be symmetric around 33, and this will be the frequency response of the desired filter. As you can see, the stop band attenuation is actually larger than 50. The stop band ripples are less than 50. But if you do this in MATLAB and find the stop band attenuation not meeting the requirement of 50, so you can go back, increase the filter length, or else you can choose a different window in order to get or meet the requirements we have. So now we have completed this part, which is designing FIR filter using the windowing method. The next part is about designing using frequency sampling method. The frequency sampling method, as a matter of fact, requires the knowledge of DFT, the discrete Fourier transform, and FFT, the fast Fourier transform. So we'll postpone it for now after we study the DFT and FFT. So this will conclude the part of designing FIR filters using the windowing method. In our next lecture, we will start talking about designing IIR filters.